Hi everybody, welcome to week 8 of Physics 2220 where we are covering the short chapter 30 on reflection and refraction. It's a short module, but optics is one of my favorite subjects of physics, so I hope you enjoy it. Over here we have a nice picture of Mount Rainier, and in a very nice, tranquil, smooth lake, you get a very nice, clear reflection of everything off the surface. So that's something we're going to talk about first off, is just kind of how reflection works and what kind of things make a better reflection and a worse one. So if you'll let me skip, there we go. So for the first concept, you have materials reflect nearly all the light incident on them. This is especially true for metals. So kind of the reason why optics comes after E&M as far as the electricity and magnetism stuff is when you saw Maxwell's equations at the end of module 2, they really produced electromagnetic waves, just the whole concept of Maxwell's equations and how they were governed. And so these electromagnetic waves are what make light propagate, and what we see with our eyes is these waves. And so if you had a metal, if you recall, they had a lot of free electrons that were they weren't trapped, so they were easy to move around. They're what screened the electric field to stay out of metals. So when you have this electric field wiggling around, interacting with, let's say this is a metal surface, all those free electrons are able to wiggle back and cancel that E field out, and by doing so produce an E field that propagates away. So you get very nice reflections off the metal because of those free electrons. And then say like if you had a plastic thing, it's normally like matte or wood, it's just very matte. You don't get a lot of reflection. You get nice diffuse reflection of like room lights off of them, but you won't see your face in them if you look down. And so the other thing then is how smooth the surface is, right? Because if you crinkle up aluminum and try and stretch it back out, you're not going to get a nice mirror reflection anymore. And that has to do with the smoothness of the surface. So if it's rough, as the rays of light come in nice and parallel and hit it, they bounce off at all these different angles. As opposed to if it is a nice smooth surface, all these rays coming in will bounce off nice and even. For concept 2, refraction results from differences. And I'll go ahead and put it in there. And when it's a nice reflection, the angle that comes in is the same as that comes out. And when you define these angles, you have your surface, you have your normal to the surface, and you always want to define your angles from the normal. So theta incident would be over here if the light's coming in this way, and theta reflected would be from the normal to this ray coming out the other side. Concept 2, refraction results from differences in the speed of light in different materials. So pretty much what you have is you have Snell's law is what's coming into effect here. Is it recording still? I can't even tell. Alright. So for different speeds, what we had is this relationship called the index of refraction, which is the speed of light over the speed in the material. So for something like vacuum or even air is pretty much the same. You get n equals 1, where essentially the light is propagating at the same speed it would if it were just an empty space. And so what happens is if you go from one to another, so like if you just have air and say this side's glass, which would be like 1.5 or something, it moves up quite a bit slower in the glass. Then you get what's called refraction, or a bending in the ray of light. So if the light comes in at this angle, it would leave at this, I'm a little exaggerated there, this slightly shallower angle. Okay. And the way that helps me know whether it's going to bend towards, right, so in this case if it goes to a higher, it bends towards the normal, right, this angle is smaller than this one, and if this was, say, if I went from n equals 1.5 to n equals 1, and I go like this, it would bend away from the normal, where this angle would then be bigger, refracted. Or, yeah. And so the way that helps me remember that is I think about, you know, you've had like an RC car or something, and you're driving it around, and you go from tile or hardwood onto a carpeted floor, right? So say you have your car, here's the axle going this way. As this wheel hits the carpet, it's going to struggle a little bit, it's going to go a little bit slower. But this other wheel, if it's still on the hardwood, it's still going to go fast. And so what happens is the axle will kind of rotate as this wheel moves slower than this one. And so the new propagating car would then be at this angle. So it kind of bends that way as it goes from the faster to the slower surface. And you get kind of the opposite effect if you go from the carpet onto the hardwood. This left wheel will hit the hardwood first. It will go faster, and so then it bends the opposite way. So then this one will bend that way as it goes. So that's just kind of how I remember and keep them straight. And Snell's law is what the equation is that you use to really quantify that change in angle, which is n1 sine theta 1 equals n2 sine theta 2, where you just quantify then n1, n2, always have your surface normal, and then theta 1, theta 2. And that's all you need. It just tells you about that change in angle going from one medium to another. And so total internal reflection results when light is incident on an interference from a medium of greater optical density to one of lesser. In this example, going from water to air. So if you've been in an aquarium, you might have seen this, right? If you have like the big aquarium and you're looking up at the surface of the water of the aquarium, you can see that it looks like just a mirror surface. And it's because of total internal reflection. And so what that means is there's pretty much an angle where if you hit it at it or greater than that, oh, that was not good. It should be the same angle. Then you get all the light reflected back inside. And if you go at a shallower angle, right, always draw surface normal, then you get the light coming back out. And it should go this way. So only when you're at or less than this critical angle will you get total internal reflection. And that's defined as this one down here, sine theta c equals n2 over n1. Where n1 is this medium that you're in, n2 would be in this case air, so n2 must be less than n1 for this to work. And then you can find this angle. And if, like I was saying, if you're ever at a greater angle, right? Oh, dang it, I drew my angles wrong. From the normal. So if this is theta c or bigger, right? So it has to be this angle or more, so coming shallower. Then you will get total internal reflection. And it's something, in the textbook they also talk about how this is what happens in a fiber optic cable. So without total internal reflection, we would not have the internet speeds that we have today, or communication in general, as far and as fast as we currently do. So it's a very good topic to know about. And so the last one here that we're going to go over is wavelength dependent refraction results in what's called dispersion. And so how we talked about the index of refraction just being c over v, we actually get a case where the index of refraction is a function of the wavelength, where the speed that the waves move in a material depends on what wavelength the wave is. And the best way to show you this is pretty much just to look at the text where they have a fun, we'll keep that, this nice plot here of refractive index versus wavelength. In this case, it's for crown glass, which is just a special kind of glass, where the higher wavelengths, or sorry, longer wavelengths, have a smaller index of refraction, which according to Snell's law would mean that if you're going from, say, a low to a high index, the bigger that change, remember, the less that's gonna, the bigger the change in index of refraction, so you're going from 1 to like 1.51, is going to give you some change. And then if you have, for like the blues and violets, a bigger index is going to bend more. It hits a shaggier carpet, so it's going to have more of a twist to it, which is what you see in this figure next to it. The reds only deflect a little bit compared to the blues or violets, which would deflect a lot. And so that's what spreads out all the colors, is that change in index of refraction across the spectrum. So, like I was saying, pretty much you use Snell's law, but you just apply each of the different indexes to know what those changes in angles are. And with that, we'll conclude Chapter 8's video. So please get going on those practice problems and the homework, and I'll see you later.